Thank you for joining us today. My name is Kathy Sheffers and I am with Goodheart-Willcox Publisher. Goodheart-Willcox is proud to support HVAC educators with quality instructional resources designed to help prepare your students for entry-level HVAC careers. Today, I am happy to introduce you to Gary Xavier, one of our outstanding authors. Gary Xavier wrote Math for HVACR, which provides a review of basic math and advanced calculations within a framework of HVAC applications. Gary was also very instrumental in the development of GW's new Follow the Heat animations, which are available with the 21st edition of Modern Refrigeration and Air Conditioning by Dan Braciano and the new 5th edition of Heating and Cooling Essentials by Don Crawshaw. Today's presentation is all about water, because if you are teaching boilers, chillers, water-cooled or water cooling, your students need to know about water. Gary has over 20 years in the field dealing with waterside issues, and he will share that experience with you today during his presentation on water and explain why water is nearly the best heat transfer medium. And this is a heat transfer business, right, Gary?
Right, Kathy. We are in the heat transfer business, and welcome everyone to water everywhere. But welcome mainly to the heat transfer business, because that's what we do. Those of you that have joined me for other presentations know that I say that a lot, but it's all we do is transfer heat. We move heat around. It's our business. It's what we do. So when we talk about water, Kathy said it correctly. Water is one of the best heat transfer mediums we use. And compared to air, compared to steam, water is the best. And I've been dealing with water a long time. Follow the heat, of course, is what we say in the heat transfer business. We move heat around, we move heat in, we move heat out, but it's all about heat transfer. So that's what we do, and water is an excellent medium for heat transfer. The line water everywhere is something that I've thought about for a long time and often found myself repeating it in a shortened version in my head as I was working. But it comes from a poem written by Samuel Taylor Coleridge over 200 years ago. His sailing ship was becalmed near the equator, not enough wind to fill the sails, and apparently they were running short of fresh water. And his lines, water everywhere, and all the boards did shrink, water everywhere, nor any drop to drink, often ran through my mind, even though I had not read the poem. It's one of the longest poems ever written. This is lines 119 through 122, if that gives you an idea of the length of that poem. But when I was working, I often thought of that. I was surrounded by water. I often joke that I spent my life in hot water, but water everywhere and not a drop to drink is what I was always thinking when I was working on the water side of the boilers or chillers. And all of that water was very useful, but not drinkable. Not drinkable at all. So I thought for this presentation, what a way to start. Let's talk about water everywhere. And we have it for all sorts of our equipment. Hot water heating systems, of course, use water as a medium. Chilled water cooling systems, chilled water, very beneficial for cooling. Water-cooled condensers. I worked on a lot of refrigeration systems that were DX evaporators, walk-in freezers, walk-in coolers, cold storage facilities, but their condensers were water-cooled because water is such an excellent medium for heat transfer. Evaporative coolers and cooling towers, water source heat pumps, all of these things use water as a heat transfer medium. Cooling towers, of course, a little different than an evaporative cooler. Oftentimes that distinction is lost on the average mechanic, but there are some differences there as well. And when it comes to the water chemistry, they may be very different pieces of equipment here. And then, of course, we have geothermal systems that can use direct contact to the ground with the refrigerant, but many of them, and all the ones that I worked on, because they were commercial industrial systems, used water, typically a glycol water mixture, because we're afraid of freezing the water solution in the ground. But the geothermal systems used water as well. So all of these systems use water as a heat transfer medium tremendous way to transfer heat. Water, though, has the potential to do damage to an HVACR system. This water in this bottle looks pretty nice. This looks like pretty pure water, and it is. It is very pure, but it is very corrosive. Water has the potential to do two things to systems. It can corrode and it can scale. And that's what made my business. I was in the waterside service business. I did it for 20 some odd years after I learned things about refrigeration and air conditioning and heating, decided to start my own business. And the reason I took my business to the water side, as I like to say, is because I found that most of the mechanics in the field, most of the contractors, most of the service companies, and most of the mechanics in the buildings did not understand the water, and they needed help with that. And I knew a little bit about chemistry and a little bit about water, so I thought, what a good way to make some business here, make some money. So that's what I did. But what I found was exactly this, that there are two potentials that do damage to our systems from the water. We have the potential to corrode the metal, what we call rust or corrosion, and we have the potential to form mineral deposits, what we call scale. So water is a tremendous heat transfer material, but it also has a tremendous potential to do damage to our systems. And that's what we want to talk about today. So even though I don't expect pretty much anyone to go into the water treatment business from this presentation, what I do expect is that anyone that works on an HVACR system that uses water as a medium needs to know about the water. They need to know the potentials of the damage that water can do. So let's talk about that.
Water chemistry. There are many commercial and industrial heating, cooling, and refrigeration systems using water as a heat transfer medium. Hot water heating systems, steam boiler systems, chilled water cooling systems, and geothermal systems all use water as a heat transfer medium. HVACR service technicians, while they don't need to be water chemistry experts, should be aware of the damage that water can do to this equipment. Water chemistry is probably one of the least understood aspects of HVACR systems, and the responsibility of caring for the water side is often left to those who sell the chemicals and equipment necessary to provide this care. There are two potentials for water to do damage to an HVACR system: the scaling potential and the corrosion potential. Water is sometimes called the universal solvent because it can dissolve anything if given enough time. As water makes its way down into the soil and rock below, it can dissolve solid rock. When that water is pumped from the ground, it carries dissolved rock. We call them dissolved solids, minerals, and all we need to do to get them back into solid form is to heat or evaporate the water. We call those solid deposits scale, and they are an insulator, slowing down and sometimes completely stopping heat transfer. That's the scaling potential. The potential for corrosion, the corrosion potential, occurs because of the corrosion triangle. Like all triangles, it has three sides: the metal side, the water side, and the oxygen side. Remove any one of the three sides and the triangle collapses, thus no corrosion. But most HVAC systems that have water also have metal, and there's oxygen in the water. There are many factors that affect the corrosion rate, but corrosion always occurs, and we can't stop it. We can slow it down, but we can't stop it. That's the corrosion potential. Proper water chemistry can protect HVACR waterside systems from both scale and corrosion. And though most technicians are not well versed in the application of water treatment chemicals, they do need to be aware of the hazards of both untreated and chemically treated water. Water is the best medium for heat transfer available to us for use in HVACR systems, and recognizing its potentials to do damage, scale and corrosion is the duty of all. Water chemistry.
There are properties of water that we always talk about in the water treatment business, that oftentimes the water treatment vendors or people that know chemistry throw these terms around almost as buzzwords sometimes. I wanted everyone watching this presentation to have a little bit of an idea of these terms and their characteristics or definitions. So I've listed some here, about a dozen of them, that I may mention as we go through the program. Things like alkalinity and calcium and chlorides and conductivity. These are all properties of water that the water chemistry people often talk about a lot. And something that we have to know is simply this: we have to be able to communicate. So if we use a vendor to take care of our water chemistry, say in a power plant steam boiler or in a school's hot water heating system, regardless of the size of the system, it needs water chemistry. They all do. And if we use a vendor or a professional water chemist to work on that system for us, we need to be able to communicate. So what I've tried to do here is show a few of those terms, things like dissolved solids and hardness, etc., with a little bit of a definition of what they're talking about. Now, when we talk about things like solids, solids cause scale, and that's our second potential that we're going to talk about. But all water, whether it will scale or not, whether it will form calcium deposits or magnesium deposits, regardless of that, water is corrosive. And corrosion is our main potential here. It's not always thought about as much as the scaling because it's not as obvious. Scale is obvious. When you see a calcium scale, a buildup of deposits on a boiler tube, it's very obvious. But what's less obvious is the corrosion that's occurring underneath that scale. And even if there's no scale, there's actually more corrosion. So the first potential of water that we want to talk about is the corrosion potential. And we can slow it down, but we can't stop it. Corrosion comes because of the corrosion triangle. And like all triangles, it has three sides: the metal side, the water side, and the oxygen side. Now, if you take any one of those three things away, take away one of those sides, the triangle would fall down. You'd get no corrosion. But you can't take the metal out of a boiler. You can't take the water out of a boiler. So in steam boiler systems, we try to take the oxygen out of the water. We do that with a deaerator. With water boiler systems, we seldom bother, but we use a chemical to try to isolate the oxygen so that it can't do as much damage. But we can't remove the oxygen atom out of the water molecule. Water is H2O, hydrogen, oxygen. So we can't get the oxygen atom out of the water molecule, but we can try to get the oxygen molecule out of the water. Water carries air with it. Air is embedded in the water. And if we can drive that out somehow, either chemically or mechanically, then we will get less corrosion. So we can slow it down, but we can't stop it. Cannot stop it. Mother Nature won't let us. Mother Nature says, I always want the metal back. I want it back as iron oxide or iron ore, so I'm going to do my best to dissolve it. And that's what corrosion is. It's a dissolving of our metal. There are several different types of specialized corrosion that we often have to deal with in the field. Here's one that is only found in galvanized steel, especially cooling towers. Galvanized steel cooling towers, very, very prevalent in the industrial and large commercial industry. If they are not properly passivated, when that metal is sent to us in the form of a cooling tower, then they will form what's called white rust. And you can see that on the center slide here, the center slip on this slide. The left-hand slip of steel there is new galvanized. The one on the right is a passivated galvanized, which is something we try to do in the field after we receive a brand new cooling tower. And if we don't passivate the metal properly, then we get that center slip in the slide there is called white rust. It looks like a powdery deposit, but it's a corrosion of the metal surface. So that's one specialized form of corrosion. There are others, of course, but that's one. And here's another one. This is on the boiler side, where this is on the cooling tower side. This is on the boiler side. This is oxygen pitting. And oxygen pitting is a severe, severe problem that we find in boilers. And this is one that often goes unnoticed until we open a boiler for inspection for an annual or a biennial inspection, whatever it happens to be. And we open it up and see something that looks like this. The first time I ever saw that, I was overwhelmed. I was overwhelmed. I opened that boiler and I saw this, and that boiler was only 9 months old. That boiler was only 9 months old, and the surface of the tubes looked almost identical to this. So that is a serious, serious type of corrosion we call oxygen pitting. So we have these corrosion issues. We have them. And it's our job as an HVACR person to try to maintain the integrity of the heat exchange surfaces. Remember, we're in the heat transfer business. And if that heat exchanger, that boiler, that chiller, whatever it happens to be, if that heat exchanger fails, we're out of business. So it's our job to maintain the integrity of that metal surface. And corrosion is our enemy. Here's oxygen pitting in a boiler tube. Now, I took this picture a year or so ago. It was called to look at a boiler in Arkansas that had failed. And when I got there, they had already taken the tubes out and actually had cut this tube apart and took a wire brush to it to clean it up. I really wish they'd left it until I got there. But when I looked at it, I saw the extent of this pitting, and had I been a little smarter at the time, I would have laid it on a white surface to take the picture. It might have been a little easier to see. But I put it on the workbench, and the workbench had a black top. So that's why the picture is the way it is. But that is a 30-year-old tube. Now, 30 years on a boiler tube is a good life. That's a good life. And that tube had served its purpose. But they didn't start to fail, and they ended up losing the boiler. They lost all the tubes in the boiler, but it didn't start to fail until their deaerator had exploded. They lost their deaerator. Fortunately, there was only one injury, and it was not terribly severe. One person was injured when the deaerator exploded. But the deaerator, or deaerator, if you pronounce it that way, or DA tank, we sometimes call it, has a job to do. And in this high pressure process boiler system, the job of that deaerator, like all deaerators, was to get the oxygen out of the water. And when the deaerator failed, they didn't replace it. And 6 months later, they lost the boiler, all because of oxygen. So those tubes might have gone another 10 years had the deaerator not failed. So we have to watch out for this kind of thing. This is all part of what we do. There are 8 factors that affect the corrosion rate on metal. And all of these factors, in some form or other, have an effect on our systems. So we're going to talk through each one of these in order. And let's start with the materials of construction. We build boilers and chillers and cooling towers and heat exchangers out of many different metals. We build them out of ferrous metals, iron and steel. We build them out of non-ferrous metals, the yellow metals, brass and copper. But metals corrode differently. When ferrous metals corrode, they flake away. They rust, the metal flakes away, they rust some more, the metal flakes away, they rust some more, the metal flakes away, and before you know it, you've got a hole in the fender of your Subaru or in your boiler tube. So they rust differently than non-ferrous metals. Yellow metals, copper and brass, when they corrode, they don't flake away. They form a green film we call the patina, and that green film actually protects that metal surface from further damage. So they corrode differently. And because of that, when we join those metals together with water around them or in them, steel pipe and copper pipe, steel boiler, copper pipe, copper boiler, steel pipe, cast iron boiler, copper pipe, when we join those dissimilar metals, we're going to get corrosion right around that junction, right around that joint. So what we try to do is we put in a dielectric union to try to keep the electrons from moving from one metal to the other, because that's exactly what happens. And that dielectric union, the non-metallic union, actually tries to minimize that galvanic corrosion that we get around that joint, but it won't completely eliminate it. What happens is this: when we use dissimilar metals in a system, one of the metals becomes the anode and one becomes the cathode. The anode, the corroded end, the least noble metals, versus the cathode, the protected end, the more noble metals. So depending on what two metals we use, let's say a cast iron boiler with copper pipe, very common for hydronic heating systems, very common for residential and light commercial buildings. So if we look at these metals on the scale, the metal closer to the top will give electrons to the metal closer to the bottom. So if we have a cast iron boiler with copper pipe, the cast iron gives electrons to the copper. So the cast iron will corrode and the copper will be protected. But if we had a stainless steel boiler piped up with copper pipe, the copper would corrode and the stainless steel would be protected, because the stainless steel becomes the cathode and the copper becomes the anode. So depending on which two metals are used, that will determine which metal corrodes. I'm sure most of you have heard of what we call an anode rod. An anode rod, a sacrificial anode, we sometimes call it. It's a rod that we use in water heaters and boilers and on ships and in the ground around underground piping or underground tanks. And that anode rod is designed to sacrifice itself to protect the other metal around it. And what's the anode rod always made out of? Magnesium or zinc. Usually magnesium, sometimes zinc, but those two metals are right at the top of that scale. They will sacrifice themselves to protect the other metal around them. What's the active ingredient in galvanized steel? Zinc. Zinc. I used to take care of the boilers at a galvanizing plant. That was one of my customers. And zinc is what they put in the galvanized steel. So the zinc can corrode and the steel does not. That's all part of the corrosion potential. But that's only one factor. There's 7 more. Oxygen is a factor. You've already seen a picture of oxygen pitting. And oxygen pitting can be very, very severe. It happens because as we heat the water, the oxygen tries to get out. And when it does, it seats itself on the metal surface. And there, right at the surface, you have the 3 things you need to have corrosion. You have the metal, you have the water, and you have the oxygen. So it causes a pit. And that oxygen pitting is very, very severe to a boiler system. So we know oxygen is a factor as well. pH stands for the potential of hydrogen ions. That's a great answer to a trivia question if you're ever asked. That's why it's a small p and a big H. The big H is for hydrogen. But the potential of hydrogen ions actually means to us the relative acidity or basicity of the solution. Solutions can be acidic, low pH, or basic, high pH. The pH scale runs from 0 to 14, at least the part we use. And the low end is called acid or acidic. The high end is called base or basic. Many people in the field call the high end of the pH scale alkaline or caustic. That's okay. Just don't confuse high pH with alkalinity because they're 2 different things. They are related, but they're 2 different things. The pH of pure water is 7, midpoint on the scale. The pH of pure water is 7. And then from that, the scientists many, many years ago determined that they could make water more acidic, more corrosive, or more basic, more corrosive. So the pH of pure water is not as corrosive as a low pH or a high pH. But for a heating or cooling system, the lowest point of corrosion is not the midpoint on the scale. The lowest point of corrosion for a heating and cooling system is generally, as pH goes, somewhere between 8.5 and 10 for most water systems, most hydronic systems. Somewhere between 8.5 and 10 is a good pH to minimize corrosion. You won't stop it, but you can slow it down by having a pH somewhere in that range. Now, for chilled water systems, generally 8.5 to 10 is a pretty good range. For hot water boilers, 8.5 to 10 is a pretty good range. For steam boilers, it might go a little higher than that, it might go up in the range of 11 or even 12, depending on the water chemistry program. And for cooling towers, it might be in the range of, say, 7 to 9. For condensate coming off of a steam system, it's generally in the range of 7 to 9, somewhere in that range as well. So this lowest point of corrosion actually moves based on pressure and temperature. But again, if we can stay somewhere just above the midpoint, just above that 7, we're generally doing a pretty good job of helping to control corrosion based on pH. Something you want to remember about the pH scale is this, that the pH scale is what we call a logarithmic scale. One whole number change in pH doesn't sound like much, from 7 to 8, for example, or from 6 to 7. But it's a huge change because it's a logarithmic scale, which means that each whole number is a 10-fold increase or decrease in pH. When you go from a pH of 7 down to a pH of 6, the water at 6 is 10 times more acidic than it was at 7. If you go 2 numbers, it's 10 times 10, it's 100 times. If you go 3 numbers, it's 1,000 times. So the pH is very, very important. And many of our water treatment programs don't watch pH as much as they used to. With some of our newer chemical formulations, our organics, et cetera, they don't watch pH as much as they used to. But it is still something we need to pay attention to because it is corrosive on both ends. At the low end, it's acidic. It actually dissolves the metal. At the high end, it's caustic, what we call caustic embrittlement. It actually embrittles the metal's molecules. So it's a different form of corrosion, but each one is damaging. So that is another factor out of the 8 factors that cause corrosion. Temperature is another factor, but it's not nearly as big as pH, but it is a factor. The hotter the water, the more corrosion you're going to get because it changes the solubility of the dissolved gases, oxygen and carbon dioxide. So higher temperature water will corrode more than lower temperature water, but it's not a huge factor. It is a factor, but not a huge one. Conductivity is a measurement of how well the water conducts electricity. Water conducts electricity. We know that from being children, when our parents taught us, don't be standing in water when you plug in an extension cord. I remember my dad telling me that a lot. So don't use a power tool when you're standing on a damp surface. So we know that water conducts electricity. Conductivity is a measurement of how well that water conducts electricity. And the more solids there are in the water, the better it conducts electricity. The fewer solids, the poorer the conductivity. So we know that solids can be an issue in our systems. We'll talk about those coming up. But the more solids we have, the higher the conductivity and the more erosion corrosion we get because of the solids working like an abrasive solution, grinding off pump seals and heat exchanger surfaces. But the lower the conductivity, the more aggressive the water is. The more things we take out of the water, the more Mother Nature wants them back. So pure water is more corrosive than hard water. Soft water is more corrosive than hard water. Deionized water is more corrosive than soft water. And reverse osmosis water, RO water, is more corrosive than deionized water. So the more things we take out, the lower the conductivity goes, the more corrosive the water is. So what we try to do is we try to stay somewhere in the middle, kind of like pH. We try to stay somewhere in the middle, but we don't know what the middle is because it's different for every system. Every system, steam boiler, a water boiler, a cooling tower, a closed loop system, they're all different because it depends on the water you're using for makeup and the chemicals that you're using. But we want to usually be somewhere in the middle. Not too low of conductivity, not too high of conductivity. That's a big factor. Pressure, that's a smaller factor. High pressure boilers, such as power plants running at 1,000 PSI or 2,000 PSI, pressure is a very big factor for them. But for our residential, commercial, and industrial boilers, we're running at a few hundred PSI or less. Pressure is not as big of an issue, but it is still a factor. Flow velocity causes what we call erosion corrosion, sometimes referred to as flow accelerated corrosion, or FAC, F-A-C. Flow accelerated corrosion is erosion. Just like the river erodes the riverbank, water running through our pipe or steam running through a steam line erodes the piping, especially valves and fittings and elbows and reducers. It erodes, and that erosion corrosion can be changed by velocity of the water, the speed of the water, etc. So flow velocity is a factor in corrosion. And then we have the fouling factor. And the fouling factor is something that's pretty obvious if you work on a steam system, not seen as much on a water boiler system, but on a steam system, we see the fouling factor quite often. We also see it in cooling towers and any other heat exchanger where we tend to get a deposit. If you get a deposit on the metal surface and it sticks to the metal, the area under the metal, the oxygen gets used up. That becomes the anode. And the rest of the metal becomes the cathode. So what happens is we start to lose metal at the surface. It starts to pit. And when you clean off that deposit, you're going to find pits in the metal. You know, I never understood that. When I first started in this trade, I started cleaning things when I started my own business. That's how I got my business going. Is I had a potential customer that said, "Hey, could you clean this? Could you clean this cooling tower for us?" And I said, "Yeah, I guess so." So I did. And then I went on to cleaning boilers and cleaning other things because I found not too many people wanted to do that. And it was a way to make a living. But when I would clean a boiler, the first few that I did, and I'm talking the water side and the fire side, but when I would clean the water side, if it had a deposit on the metal that I had to scrape off or chemically remove, under that deposit, it was corroded. And the part of the boiler that didn't have the deposit stuck to the metal was shiny smooth, no corrosion. So I did a little research and found out, yeah, it's under the deposit, which made sense then. So the trick is to keep anything from sticking. We get sedimentation. We get sediment in steam boiler system, but we should not in a water boiler system. We should not get sedimentation. But we do in a steam boiler system, we do in cooling towers. We know that and we deal with it. The trick is to not let it stick. If, as long as it moves around, it might settle to the surface when the boiler shuts off, or when the boiler starts back up, starts moving around again. That you won't get the corrosion underneath it. But if it sticks, then you get the corrosion. So those are the 8 factors of corrosion, and we can't stop it. We can slow it down, but we cannot stop it. Those are the corrosion factors. There's another potential for water to do damage, and that potential is called the scaling potential. The scaling potential means water can leave deposits behind. And we've all seen that. We've seen it in Grandma's tea kettle when she would heat water on the stove to make her a cup of tea. Eventually that tea kettle weighed more empty than it ever did full because it had all these mineral deposits in the bottom. We see it in boilers. We see it in cooling towers. We see it in water heaters. We see it any place that we heat the water or evaporate the water. The minerals can come out. Water is often called the universal solvent. Water can dissolve anything if you give it enough time. Water goes down through the ground and dissolves rock. So if water can dissolve rock, is a boiler a challenge for water? No, not at all. Water can dissolve boilers too. But when water dissolves the rock, and then we pump that water out of the ground, we get that rock back in dissolved form. We call it a dissolved solid. It's still rock. It's still mineral, calcium, magnesium, silica, iron. Those are all dissolved minerals that we find in our water. But all we have to do to get that dissolved solid back into solid form is either to evaporate the water or heat the water. What does a boiler do? It heats the water. What does a cooling tower do? It evaporates the water. A steam boiler heats and evaporates the water. That's a terrible situation for a scaling problem. A cooling tower simply evaporates the water. A water boiler simply heats the water. So anything we do in our trade, we can get scale out of that water. But we can stop that. We can stop that scale. Here's a picture of a chunk of scale. I didn't take this photograph, but I've taken scale out of boilers that look just like this. I had one boiler situation that we got called in where the boiler was in serious condition. It was still running, which was unbelievable to me. It would still work, but it had inches of scale throughout. We actually had to cut the boiler apart and chisel the scale out and then weld the boiler back together. That's how we were able to do that. And it cost them almost as much as a new boiler. And why they didn't just buy a new boiler, I'll never know. I tried to convince them to do that, but they said, well, you don't sell boilers, so we want you to do the work. And I said, well, okay, we'll take your money. But we cut the boiler apart, chiseled the scale out, and then welded the boiler back together because we knew what that scale would do. That scale is an insulator. It's an insulator. Think of the insulation value, the R value, for a chunk of scale like this. Scale inhibits the heat transfer. And when it does, it also causes corrosion underneath. So it's a two-edged sword, so to speak. If we get the scale, we're definitely going to get more corrosion too. So we try to prevent that as best we can. Here's an example of the heat transfer loss with scale. This is an example of a high pressure boiler tube. Now this example, the boiler was running at 585 PSI approximately. And so to be up to 585 PSI, high pressure steam, 486 degrees is the saturation temperature of water at that pressure. With a clean tube, as you can see in this little drawing, with a clean tube, the fireside tube temperature was just shy of 600 degrees, 599 degrees. Now, keep in mind, we're in the heat transfer business. Heat transfers from a warmer thing to a cooler thing. So the fire is the hottest thing. Natural gas burns at about 1500 to 1800 degrees Fahrenheit. So let's say this is a gas boiler. So 1500 degrees. So the fire is 1500 degrees. The fire gives heat to the metal tube of the boiler, the heat exchanger, the metal tube. That tube heats up to 599 degrees, and the water then gets heated around the tube or in the tube. This was a water tube boiler example. So the fireside tube temperature was 599, and the water temperature inside the tube was 486 degrees. That's with a clean tube. Now put a 1/16 of an inch of scale on that tube. A 1/16 of an inch, the smallest mark on your tape measure, a 1/16 of an inch. Now, you put a 1/16 of an inch of scale on that tube. Look at what happened to the water temperature. Nothing. Because the boiler still needs to run at the same pressure, so the water has to be the same temperature. But to get that water to that same temperature, that boiler burner had to run 12.4% longer on every firing time. It had to run 12.5% roughly, more than it did before. So your fuel consumption is affected dramatically because the scale is an insulator. But that's just part of the problem. Look at the tube side temperature. To get the water to the same temperature, the tube had to be hotter because it has to force the heat through that insulation of the scale. And the tube side temperature went up to 800 degrees, 201 degrees hotter than it should be. And that tube couldn't take it. That tube could not take the extra heat. And look what happened to it. This tube failed. It split wide open from being too hot. Scale on the inside, as you can see here, fire on the outside, and is a water tube boiler. This is a tube failure. But if you think it's just a tube failure, you're very, very wrong. This is a boiler explosion. This is a boiler explosion. Why? Because the water inside that tube was 486 degrees Fahrenheit. And when that tube split, that water at 486 degrees hit atmospheric pressure. And when it did, at atmospheric pressure, the boiling point's 212. That water was over 400 degrees. it flashed to steam instantly inside the tube and blew the boiler apart and probably blew the building down around it, because water tube boilers are generally pretty good size in something like a 500 psi boiler. So this is a boiler explosion, all caused by scale, a 1/16 of an inch. Fire tube boilers are very forgiving of scale. I've cleaned fire tube boilers that had several inches of scale on the tubes, but water tube boilers won't tolerate it. So there's a big difference in heat exchangers, big difference in heat transfer there, but scale is a problem. Look at this pipe nipple. This pipe nipple completely, almost completely closed off, completely occluded there. I've seen this happen a lot of times in low pressure steam or hot water, where untreated water goes into the boiler, and right at the point where the untreated water hits the hot boiler water, the scale starts to come out and it plugs off the makeup line. That's what this apparently was. But again, scale is a problem. So we can stop that. We can stop that. We can even stop that with a water softener. That's all you have to do to stop the scale. You just have to take the minerals out. But when you soften the water, it's more corrosive than it was when it was hard water. So water has to be in balance. There has to be a balance between scale and corrosion. Mother Nature says everything has to be in balance. So if you stop the scale, the corrosion gets worse. If you minimize the corrosion, the scaling gets worse. So what do we do in our business? What do we do in the heat transfer business? We stop the scale and control the corrosion. And we can do that in boilers, but in cooling towers, can't. Because cooling towers are predominantly made out of galvanized steel, and soft water is so corrosive, we cannot soften the water for a cooling tower. So they're handled differently than a steam boiler, for example. Even though they do the same kind of thing, they evaporate water because of their difference of materials of construction. We treat them differently. The water treatment business is very involved. It's why I turned my business in that direction 40 years ago, was to take advantage of that, so to speak. There weren't many people doing waterside service in my area for boilers and chillers and cooling towers and things like that. Oh, there were a lot of mechanical contractors. There were a lot of guys doing what I could do, fixing it mechanically. But many of them then used me as a subcontractor to take care of the water side. And these are the kind of things that I found. That's the scaling potential. So what we've seen here is water has the potential to do damage to an HVACR system. And it's up to us as instructors, as mechanics, as technicians, to make sure we understand that. That doesn't mean we have to be a water treatment specialist. It doesn't mean we have to take our business in that direction or get a job with a company that does that. What it means is it's up to us to inform our students, inform our customers, inform building owners of the potential for water to do damage to their system. We all need to know a little bit about it. And that's what this program was designed to show you. It's just a little bit about it. When we talk about learning new things, I want to share something with you that I just saw last week. I saw this. I just got it. I just got my copy. I did not write this. So I'm not promoting a book here that my name's not on the front of this. Right? But I'm a firm believer in learning as much as I can learn about anything. That's the way I've always been. I love to share information. I love to learn new information. And I'm going to say something, folks, and that's this, that when I saw this book, I was pleased and amazed by it. It's a brand new book from my friends at Goodheart-Willcox that did my math book. And so I was able to get a copy of the new hydronic heating book by, I don't want to say his name wrong, Don Stevie. I don't know Mr. Stevie. I may have met him. If I did, I don't remember. He probably doesn't remember me either. Don't know if we've ever met. But I love this book. I've spent the last week several times flipping through it. I have not read the thing completely, but he does an excellent job of explaining water systems, hydronic heating systems, steam boilers and water boilers. So again, I just wanted to take a moment as I kind of pause here, catch my breath as we talk about scale and corrosion, to just mention that, because in my opinion, it's an excellent text, an excellent text. So with that in mind, here's the kind of thing that we need to worry about in our boiler systems, our water chemistry. Water chemistry for hot water boilers and chilled water loops, closed loops of any sort, is pretty simple. It's pretty simple compared to water treatment for a steam boiler or a cooling tower. With a closed loop, you're going to get corrosion, but you should not get scale formation. The reason for that is simply this, that you don't replace the water. Think about this. Many of you have probably replaced a water heater in your career. You had a water heater that was leaking, or if it was electric, the electric heating element burned out, and you decided to replace the water heater. And when you took out the old one, it weighed 3 times as much as the new one. Well, I always say, well, that's because the old ones were made better. Well, maybe, but the reason the old one weighed so much more, and you know this, it was full of junk in the bottom. It was full of scale, minerals from the water. Because as you heat the water, the minerals come out and drop to the bottom. They form scale or sludge or sediment. Now, why doesn't a water boiler do that? Because it's the same water over and over again. A water heater is different water every day. But a water boiler, as long as it doesn't leak, is the same water over and over and over again. So is a chilled water system. So as long as we don't have leaks, we don't get scale, but we get corrosion. So the water chemistry programs that we use for closed loops is typically just a corrosion inhibitor. Now, the chemical that you buy to put in that boiler or put in that chilled water loop, that chilled loop, might say scale and corrosion inhibitor. Yeah, there's a little bit of phosphate in there usually to take care of any minerals that want to come out of solution. But it's primarily a corrosion inhibitor. And we use different things to do that. We use different corrosion inhibitors. There's 2 main ones that we use a lot. We use sodium nitrate and sodium molybdate. And then we mix with them things like sodium borate, 20-multein borax from Boron, California, and a little bit of what we call TT, tolutriazole. But those are corrosion inhibitors. The borate raises the pH because the nitrite is an acid. It's acidic. Same way with the molybdate, but we use sodium hydroxide mixed with that one usually. So you don't need to be a chemist to think about these things. Just realize that when you buy that gallon jug or that 55-gallon drum of corrosion inhibitor for a hydronic heating system, for a closed loop, a water boiler, that you're getting some sort of a corrosion inhibitor there. What it's doing is protecting the metal from corrosion. Those are what we call filmers. Both the molybdate and the nitrite are what we call filmers. They lay a film of chemical on the metal, and that film of chemical keeps the water from touching the metal directly. It's like a coating, and that keeps the oxygen away from the metal. If we can keep the oxygen away from the metal, we don't get corrosion. What we don't want is too thick of a film of chemical, because then it becomes an insulator. So it's a thin line, pun intended, that we try to maintain here. But that's what we do in closed loop systems. Now, with all chemicals, whether they're for steam or hot water, just a safety note here. Always read the label and read the safety data sheet, what we used to call them MSDS, a material safety data sheet. Read the safety data sheet before you ever open that container. Follow the label instructions and the information on the safety data sheet for your personal protective equipment, for how you handle the material, how you store the material. If it says dilute it with this much water, make sure you follow that. One of the things that I noticed in my years in the field was that some people seem to have the inclination that if this much chemical is good, this much chemical must be great. If I use more, it'll be even better. No, more is not better. That's terrible grammar. I know. I know because I was told that. One of the first books that I did years and years ago, one of the first things I wrote, I used that phrase, more is not better. And I got a note from the editor as they were editing this book and said, you can't say that. More is not better is terrible grammar. And I responded to her by saying, that's how I talk. And that's what I want to say. More is not better. And I want it all in capital letters. And so we traded messages back and forth for a bit. She was in one office, I was in another. But we traded messages back and forth for a bit. And I finally got my way. And so when that book came out, there was in all caps, a line in there that said, more is not better when it comes to chemicals. So more is not better, not always. So make sure you read the label, follow the directions, and wear your PPE. Make sure that you read on the safety data sheet what type of gloves, whether they're rubber, nitrile, Viton, whatever they happen to be, because different materials have various permeabilities of chemicals. So some chemicals will permeate rubber gloves, but they won't permeate nitrile gloves. So you have to make sure you wear the right PPE. So be safe when you're around these chemicals. There's a reason they have that triangle or a diamond on the side, not a triangle, the diamond on the side that shows us their flammability, their reactivity, etc. There's a reason for that. So pay attention. Pay attention to that. If you look at that chemical safety placard, you want to make sure you're aware of what each one of those numbers tells us. So read that, understand it, and always follow your label directions. Our hydronic heating systems and cooling systems, chilled water, hot water, often use antifreeze, but we don't call it that. We call it glycol. We call it glycol so that the people that use antifreeze in their automobile engines don't think they can put the same stuff in our heating system. It is similar. They're both glycol. But since the automotive industry typically calls it antifreeze, we call ours glycol to make sure people realize there's a difference. And the difference is not in the base material. The difference is in the corrosion inhibitors that are mixed with it. Automotive antifreeze generally uses sodium silicate as a corrosion inhibitor. We don't use that because we don't have aluminum in our systems very often. And sodium silicate is a tremendous corrosion inhibitor for aluminum, but not as good on steel or on cast iron or things like that. So we use generally dipotassium phosphate. So it's a different corrosion inhibitor. So we call ours glycol. It's still an antifreeze solution, but we call it glycol. We use ethylene glycol, we use propylene glycol, but you want to make sure if you are adding glycol to a water system, heating water, chilled water, we don't use it with steam, but heating water or chilled water, make sure you're using the proper glycol and that it's an HVACR inhibited glycol. You can see some of the different ways we can buy it, anything from a gallon jug on up to a tank truck. I used to buy the tank truck for my business, and sometimes in 55-gallon drums. But we used a lot, okay? We put in a lot. But this is the kind of fluid that you want to use. There are two types, ethylene and propylene. You've probably heard of both. Ethylene glycol is the older one of the two. Propylene, or sometimes called polypropylene glycol, is the newer one. Ethylene glycol is very toxic. Propylene glycol is commonly called food grade. But glycols don't transfer the heat the same as water. They're slightly less heat transfer coefficient than water. So they don't do quite as good a job as plain water for heat transfer. They're close, very close, but they do expand at a greater rate. They also pump differently because they're more viscous. So a system that was designed for water, you can't just throw glycol in there and say, okay, I'm just going to use glycol now. You need to make sure the system was designed to handle the differences between the water and the glycol. So you have to watch out for that. Ethylene glycol, highly toxic, as I mentioned before. Ethylene glycol is what my father referred to 70 years ago as permanent antifreeze. When they started putting it in automobiles back in the 1940s, they called it permanent antifreeze because it replaced alcohol that was not permanent. And so ethylene glycol was used for years and years. It still is used some, but because it's so toxic and not environmentally friendly, that we've tried to minimize its use now. So we've gone more to propylene glycol, and propylene glycol is non-toxic. I wouldn't suggest drinking it, but you will find that it's used in a lot of our food products in small quantities. There will be polypropylene glycol in medicine, in peanut butter, in jelly, in mayonnaise, different things. There may be a little bit of propylene glycol, polypropylene glycol. They use it as a food additive. So it is relatively safe, and we use it a lot now. It doesn't transfer heat quite as good as ethylene glycol. It's very close, but not quite as good. But it is a better alternative. So if you have a system that you say it's using antifreeze, quote unquote antifreeze, it's probably propylene glycol. Glycol, when it's mixed, needs to be mixed with ultra pure water. You want to get good freeze protection, but you don't want any problems with any of the solids in the water. So you don't want to mix your glycol with tap water. If you buy it pre-mixed, it's mixed with deionized water. But if you buy it full strength and mix it yourself, you want to make sure at the very least you use soft water, not hard water. Soft water will be okay. Deionized water is better, but soft water will be okay. And then when you look at the freeze point versus the burst point, freeze point is the temperature at which we start to get ice crystals in the water, in the solution. Burst point is the point at which it freezes solid and breaks something. So when I treated systems with glycol, I didn't care anything about burst point. I wasn't going to let the system sit there and freeze up. We were running the systems year round. So we needed to make sure we didn't get any ice crystals in the solution. So we protected to freeze point. Burst point, I didn't pay any attention to. As you can see from this slide, to get you to negative 30 degrees Fahrenheit for freeze point, you need a 50-50 solution of either ethylene or propylene glycol and deionized water. That's typically what the job specifications called for on the systems that I serviced. They generally, the design engineers called for a 50-50 solution of either ethylene or propylene, and they would specify which one, but it was usually a 50-50 solution, which got us down to negative 30. Now, I worked in the northeastern United States, where we typically get temperatures that can be up in the mountains of New York State, where I had several customers, quite a few as a matter of fact. They would quite often see a whole week of negative 20 degrees Fahrenheit or negative 25 degrees Fahrenheit up in the mountains. Well, we wanted to make sure we were protected down to negative 30. And in some of those cases, we even took them down to negative 40. It all depended on the system. And negative 40 requires about a 55% solution of ethylene and propylene. So we would take them down even lower. Regardless of that, you want to make sure that you are protected from freezing. So that's what we do. And we use a refractometer or a hydrometer to actually test our fluid. We can use either one. I used both. This is a refractometer. This is a hydrometer. I used both depending on what I was checking. But these are test instruments that we can use to tell us the freeze point of that solution. Glycol is corrosive. Laboratory grade glycol is pure glycolic acid. It'll eat metal. But if it has the right corrosion inhibitor in it, then we're protected. So you always want to make sure you're using a good quality HVACR inhibited glycol. Don't use laboratory grade glycol. I saw that used just once. It destroyed the system. And don't use automotive antifreeze. And then make sure that if your freeze point is at a temperature where you have at least a 25% solution of glycol, your corrosion inhibitor is probably okay. If your freeze point is at something less than that, where your percentage is maybe 10% glycol or 20% glycol, you may have to add some additional corrosion inhibitors to that. Glycol is very, very important. If it's done properly, put into a system properly, it'll last for 20 years. It'll last practically forever if we don't do anything to damage it. If we don't dilute it with plain water, if we don't add stuff that's not supposed to be in there, add other chemicals to it, it'll last a long, long time. So take good care of your systems. And if they have glycol, make sure you pay attention to that. Corrosion protection with your glycols, as I said, is typically dipotassium phosphate, not always, but usually dipotassium phosphate. So we don't put any of the other corrosion inhibitors in with that. Always use the specified corrosion inhibitor from that manufacturer. And then make sure that everything is compatible. Watch your pH. On a glycol system, you want a pH of above 8.5, somewhere between 8.5 and 10 usually is excellent for your glycol. Also make sure that you're not taking on fresh water. The way I got in the glycol business was that a potential customer called my office one morning and said, "Hey, do you know anything about glycol?" And I said, "Yeah, a little bit." "What's up?" And he said, "My water source heat pump system froze up last night and it's full of glycol. I don't know why it froze. I broke 3 heat pumps." So I got in my truck and I drove up. And sure enough, he was right. He broke 3 heat pumps, but he was wrong. He didn't have any glycol in the system. And I said, "You don't have any glycol in here. I tested it. You don't have any glycol. You have plain water." And he said, "Wait a minute. There's the empty barrel. They put 55 gallons of glycol in this thing when they filled it up 3 years ago." And I said, "Look up. You got to make up water line. You got to make up water line. The valves are open. You got a pressure reducing valve. So as the system leaked, it took on fresh water. You've diluted all your glycol over 3 years. You lost every bit you had. So we don't want that. If we have a glycol system, we generally shut off the makeup water. That way we don't get dilution. We don't freeze up. And instead, we may put in something that looks like this, a mixed tank to add glycol if the system loses fluid. And in this tank, we put whatever we want for that glycol solution, 50-50, 40-60, whatever we want. We put in that tank. And then when the system runs low on fluid, it turns on the pump and it pumps more in. The system needs to be leak-free. ASHRAE, the American Society of Heating, Refrigerating, and Air Conditioning Engineers, says that a closed-loop system should not lose more than 5% of its fluid per year. 5%. Anything beyond that is not a closed system anymore. So they need to be leak-free. They're always going to drip a little bit. A valve, a fitting, something's going to lose. You're going to lose a little bit somewhere. But make sure they're as tight as possible. And that'll avoid problems. Glycol, as I said, is very corrosive. If you look at these corrosion test results, look at plain water, and then compare that to uninhibited ethylene glycol. Uninhibited ethylene or uninhibited propylene are more corrosive than plain water because it's glycolic acid. But if you use an inhibited ethylene glycol or an inhibited propylene glycol, your corrosion is minimal, almost none, almost none. That's in mils penetration per year. Mils is thousandths of an inch. That's thousandths of an inch. So very, very low amount of corrosion if you use the right glycol. Now, if you have to add glycol to a filled system, but your solution's too weak, let's say that your solution is supposed to be 50-50 and you find out it's 40% glycol, then you're going to have to take some of that 40-60 solution out and put 100% glycol back in. That is something we have to do. And there's a formula for that. In this example, if you've got 1,200 gallons, this is a sizable system, 1,200 gallons, and you want 50% propylene, and you actually check it and you got 48%, you might think, well, that's not bad. I just got to add a little more glycol to it. It might surprise you as to how much solution you have to take out and how much 100% glycol you have to put in. It amounts to 46 gallons. To get that up from a 48% solution to a 50% solution, you've got to take 46.15 gallons of solution out and put in 46.15 gallons of 100% propylene. It's more than you might think. Now, what if it was too strong? If it's too strong, you're going to have to take some solution out and add plain water. Once again, same system, 1,200 gallons. I want a 50-50 solution, but I measure it, I test it with my refractometer. It says, oh, you got 55% glycol. Ooh, that doesn't transfer heat as good as 50%. Maybe I'll leave it, but maybe I won't. Yeah, maybe I better change it. So how much do I have to take out to lower that glycol percentage by 50% and add plain water? It might just surprise you. It's almost 110 gallons. 109 gallons of solution that have to be drained out. Solution that is 55% glycol. Valuable product, but I can't use it in the system. So I've got to take out 109 gallons and put in 109 gallons of water to get that back to a 50-50 solution. So there are formulas that will show us how to calculate this. When I first started working in this glycol business, I didn't realize that Dow USA had some formulas. Dow is the maker of most of the base for our glycols, that they had some formulas that they had figured out to use. And I just did it kind of like, let's take out 10 gallons and see what happens. Ooh, that didn't work. Take out another 10 gallons. It took a while until I figured out that there's got to be some way to calculate this. So I played around with it a little bit, and guess what? I came up with a formula too. It worked. I came up with a formula. So those formulas are available to you. They're on page 120 of another book that I like. And this one I really do like because it's got my name on the front. But they are in there, along with a lot of other formulas that we use in the Math for HVACR book. So they are there. And if you're interested in that, of course, if you get a hold of my friends at Goodheart-Willcox, they'll see that you get a copy of that. So you can get those formulas. That's our glycols. Steam boilers and cooling towers are tougher. When I got rid of my service business, we were servicing hundreds of systems under contract to us. And I used to joke that we don't make any money on the water systems. We don't make any money on the water boilers. We don't make any money on the closed loops. We did. We made a few bucks. But where our bulk of our income came from was steam boilers and cooling towers, because they are problematic. They're very different from a water system because they don't use the same water every day. A water boiler, a chilled water loop, uses the same water over and over again as long as there's no leaks. But cooling towers and steam boilers evaporate water. So even though they're very different systems, we chemically treat them similarly because of the evaporation. What happens with a steam boiler or a cooling tower is we concentrate solids in the water. We concentrate the solids. And there are different types of solids that we have, dissolved solids and suspended solids. But as the water evaporates, the solids stay behind. And those solids concentrate and can form scale. Dissolved solids and suspended solids are very different, but they both cause problems. Think of it like this. If you happen to be a coffee drinker and you happen to put sugar in your coffee, you know what a dissolved solid is. Because when you take that cup of coffee and put a spoon of sugar in it, the sugar is a solid, and you stir it up and it dissolves. It's still in there, but it's a dissolved solid. Now, if you were to put 4 spoons of sugar in a standard sized coffee cup, you could stir all day and it won't all dissolve because the coffee can't hold all of it. Some of it would just float around and drop to the bottom when you stop stirring. That's like a suspended solid. Suspended solids don't dissolve. Now, some suspended solids are leftover dissolved solids that couldn't dissolve because the liquid couldn't hold them. We had reached our solids loading. But some dissolved some suspended solids will never dissolve. Some things will never dissolve. So in your water, you have both. And they concentrate as you heat the water or evaporate the water, the solids concentrate. And that's what we call cycles of concentration or concentration of solids. Think of it like this. If you had 3 solids in your water coming into your boiler, let's say, now you're going to have more than that. But I have a limited number of fingers here, so I'll say 3. So you've got 3 solids coming into your boiler. When you turn that water into steam, what happens to those 3 solids? Do they go out with the steam or do they stay in the boiler? They stay in the boiler. The steam is pure distilled water, just hasn't condensed yet. So there's no solids in the steam. So the 3 solids stay in the boiler. But you made some steam, so you need to bring in more water. So you bring in 3 more solids. Now you've got 6 in your boiler. They're starting to concentrate. And you make some more steam and you bring in some more water. And now you've got 9 solids in your boiler. Now I'm going to stop because I'm out of fingers. But I'm at what we call 3 cycles of concentration because I've got 9 solids in the boiler and I'm bringing them in 3 at a time. And 9 divided by 3 is 3. So I'm at what the water treatment people would call 3 cc or 3 cycles or 3 cycles of concentration. Now, if my water treatment vendor, my provider, my expert in water chemistry said, hey, I don't want you to have more than 10 solids in your boiler. What do I do now? I'm still making steam. I'm going to get 3 more solids. I'm going to have 12, and I don't have enough fingers for that. So what am I going to do? I'm going to let some water out. I'm going to do what we call blow down or blow off, and I'm going to send some water with 9 solids down the drain and replace it with water with 3 solids. So now I'm back to 6 or 7 or 8, but I'm more than 3 and less than 9, and I'm controlling my cycles of concentration. That's what we do in a cooling tower or a steam boiler. By doing blow down or blow off or bleed off, we call it different things, but by letting water that has a lot of solids in it go down the drain, then we can replace it with water with fewer solids, and we maintain a concentration of solids that we want. It looks like this in a boiler. I've got 3 solids here. You can see them, 3 little dots there, 3 solids. That's 1 cycle of concentration if I've got 3 solids in my water. And then all of a sudden, I make steam. And wow, look at the solids. You can count them if you want. I'm at 15 cycles of concentration. I got 45 solids in there now. And then I open a valve and I take some water out of the boiler. I do some blow down and I'm back to 10 cycles. So that's what we do. We maintain a certain level of concentration of solids. Now, why don't we just leave that valve open and just always have 3 solids in the boiler? We could do that. Same thing with a cooling tower, we could do that. So why don't we do that? Because every time we send that water down the drain with all those solids, we're using more water, which costs us money normally. We're using more chemical, which always costs us money. And in the case of a boiler, we're using more fuel because the water going down the drain is heated to steaming temperature and the water coming in is not. So I have to heat it back up. So we're sending money down the drain every time we open that valve. So we try to maintain as high as possible cycles of concentration in both a boiler and a cooling tower. We try to maintain the highest level cycles of concentration we can, which we measure by conductivity. The more solids in the water, the better it conducts electricity. So by measuring our conductivity, we can then tell how much solids I have in the water. And when I do my blow down, I control that. We can blow down off the top of a steam boiler. We call that surface blow down. Really isn't at the surface, it's just below it. Or we can blow down off the bottom. We generally, in high pressure steam, do both. Low pressure steam, maybe just off the bottom. But that's how we control our solids. We control our solids by getting that water with all the solids down the drain. We do the same thing in a cooling tower, but the cooling tower water is not heated, but it's evaporating. So the same thing happens. Here you can see it in the sump of the cooling tower. 3 solids, 1 cycle of concentration, it builds up, and we drain some off. So we have to get rid of those solids. That's what makes the water chemistry programs for steam boilers and cooling towers so different than it is for water boilers and chilled loops. Both of them require water chemistry, but the water chemistry for a steam boiler or a cooling tower is much more extensive and much more expensive than it is for a closed loop system. That then is coupled with the chemicals that we use for our steam boilers. We use different chemicals for them than we do for our water boilers, and we use different chemicals for our cooling towers than we use for our steam boilers. There are a lot of different treatment programs out there, and the correct program for any system is always based on, first and foremost, the quality of the water coming in. Then we look at the type of system, the size of the system, the pressure, the temperature, the amount of water makeup we have, etc. And from that, the water chemistry people then come up with a prescription, so to speak, a program of how to take care of that piece of equipment. Water chemistry is very, very important. It is a specialty within our trade. I specialized in that because I found that that was a good way to make a living in my area. It is a specialty, but we often use a vendor to do that. We use a water treatment vendor, a chemical vendor to help us with that. Regardless of that, it's our responsibility as instructors, as students, as technicians, as building owners. It's always our responsibility to make sure we understand the potential of that water to do damage to our HVACR systems. I've been teaching for a number of years, about 25 now. But for the 25 years before that, when I was a mechanic and had my business, I was still a teacher because I was always trying to explain to people that owned the systems that I serviced why this water was doing such damage to their system. And that's what we do. We share information. So I tried to explain to my customers who were building owners and operators, stationary engineers and building mechanics, etc., tried to explain to them why they had to take care of that water. Because if they didn't take care of it, it couldn't take care of the system. And the system couldn't take care of itself. So it's all of our responsibility, every one of us, to understand the potential of water to do damage. And that's what this program is for. I thank you for your time. I hope that you have picked up a little bit of information here. And again, folks at Goodheart-Willcox are very good at sharing information. So thank you.
Thank you, Gary, for another wonderful presentation. As I was listening to your presentation, I was noticing a lot of key terms such as temperature, measurement, fractions, percentages, conversions, formulas, and I kept thinking about your math book. So I know that you had mentioned that instructors can contact Goodheart-Willcox if they'd like a sample of the book. I also appreciate you giving your impression of the new hydronic heating book as you're talking about water systems. So I know Don Stevie will appreciate your interest in the book, and we'd be happy to share that with other instructors out there as well. So thank you again, as always, for representing Goodheart-Willcox. Thank you for the great math book that you've created for our instructors, as well as your Follow the Heat animation. So to everybody out there, thank you for attending this session. And to Gary, thank you for presenting it so well.
You're very welcome, Kathy. Thank you.